morning to one and all. I'm Venkatesham. I'm going to discuss about the colligative properties. In this video, I'm going to explain the colligative properties. So, colligative properties are the properties of a dilute solution, which are directly or indirectly depends upon the number of solute particles which are present in the dilute solution. Right? So, properties depression in depression in freezing point. This depression in freezing point is another third colligative property. So first we'll discuss about this freezing point. What is mean by a freezing point? So freezing point. So freezing point, before actually what is a freezing? Freezing is nothing but the process of converting the phenomena in which there is a liquid is converting into the solid is it's a freezing, right? So the freezing point is nothing but the temperature at which there is a liquid vapor pressure should be is in equal to the it's a solid vapor pressure if both liquid and solid are in a dynamic equilibrium, and the vapor pressure of liquid should be equal to the vapor pressure of solid at a particular temperature. That particular temperature is it's a freezing point. So freezing point is simply at the temperature at which vapor pressure of a liquid is in equal to the vapor pressure of the solid when both liquid and solid are exist in a dynamic equilibrium, right? So this is a simple freezing point and suppose I am taking that in one beaker and here solvent is taken. This solvent vapor pressure is it is P naught and this solvent freezing point I am taking is a TF naught. TF naught is a freezing point of a solvent. TF naught is a freezing point of a solvent. For this, if you add any non-volatile solute is added to this one. If you add some non-volatile solute to the solvent, then it forms a solution. The solution and vapor pressure will be decreases. I am taking that solution vapor pressure as a PS, and this solution definitely will have the certain freezing point. That freezing point I am taking is it is TF. TF is a solution freezing point after adding the non-volatile solute, whereas a TF naught is a freezing point of the particularly it's a pure solvent. As all we know that there is a vapor pressure of the pure solvent P naught is always greater than the PS, because when we are adding the non-volatile solute, some of the solute molecules are replaced with the solvent molecules in the surface. That's the reason it's the vapor pressure always decreases for a solution. Whereas in the case of this particular freezing point, when we are adding the non-volatile solute, the freezing point of the solution is decreases. That's the reason we can write this is TF naught is always greater than the here TF. When we are adding the non-volatile solute to the solvent, the freezing point of the solution is decreases because it is having there is a less vapor pressure, so that definitely it's the temperature required also less. That's the reason it's a freezing point will be decreases. The decrease in this freezing point of the solution is it's a depression in freezing point. What is a depression in freezing point? The depression in freezing point is nothing but when we are adding the non-volatile solute to the pure solvent, the solution vapor pressure will be decreases, and definitely it's a freezing point of the solution also decreases compared with the pure solvent freezing point, and that's the reason we'll write here freezing point of the pure solvent is always greater than the it's a freezing point of the solution, and always the freezing point of the solution will be decreases when we are adding the non-volatile solute. The decrease is actually it's a depression in freezing point. The depression in freezing point mathematically we'll write this is a delta TF is equals to this is a TF naught minus this is a TF is a difference between the freezing point of your solvent to freezing point of solution is a depression in freezing point. Relation between the delta TF and molality, depression in freezing point and molality. For this you need to plot a graph here. Vapor pressure is taking on the y-axis and the freezing points are taken on the x-axis. Then you will get that here it is clearly this is a solvent vapor pressure, this is a solution vapor curve, solvent curve, and this one is a solution curve. So and this is particularly TF not. This difference is actually it is a delta TF. Take this one as a PS and this one is a P naught. This difference is a delta P. If you plot a graph between the vapor pressure to the its a freezing point for the solvent and solution separately, this is a solvent curve and this is a solution curve, right? So this solvent curve and its a freezing point is a TF naught, and a solution here solution freezing point is a TF, right? And this solvent vapor pressure is a P naught and a solution vapor pressure is a PS. From this graph we can conclude that there is a delta TF is directly proportional to the it's a delta P, and we know that from the Raoult's law. Let us take this is equation 1. There is a delta P is directly proportional to the x1. Let us take equation 2. Delta TF is directly proportional to delta P. Delta P is directly proportional to the x1. From equation 1 and 2. From equation 1 and 2, we can write this is a delta TF. So which is directly proportional to the x1. Okay. From this equation 1 and 2, delta TF is directly proportional to x1, and here delta TF is equals to this is k into x1, where k is a simple constant from the classical thermodynamics as here k is equals to this is r T naught F square divided by this is LF. LF is a molar latent heat of freezing. Molar latent heat of freezing is nothing but the amount of heat absorbed for conversion of 1 mole of a liquid into the its a solid state, and that particular amount of heat is a molar latent heat of freezing, and it can be represented by a symbol LF. If you substitute this one in the above equation and you will get this is a delta TF is equals to this is a R TF naught square, so divided by this is a LF, and I can write this x1 is a mole fraction of solute, and will write only here n1 by n2 only, will not write in the denominator n1, because these all the colligative properties are applicable only for a dilute solution. A dilute solution denominator n1 is neglected, right? So that this n1 and n2 you can substitute, will get this is a delta TF is equals to this is a R T naught F square divided by, and it is in LF. N1 I can write this is a W1 by M1, here it is a M2 divided by, here it is a W2. Okay, to introduce this molality term in this expression, and this equation is right side is multiplied and divided with 1000, and here delta TF is equals to, here it is a R T naught F square into this is a M2 divided by, here it is a 1000 LF into this is a W1 by M1 into this is a 1000 divided by, here it is a W2. So if you cancel this one 1000 and 1000, again you will get a above equation, and this whole term is a molality, and this term is taken as a it's a KF. KF is nothing but cryoscopic constant. This cryoscopic constant R TF naught square into M2 divided by, here it is this is a 1000 LF. This is a cryoscopic constant. I can write here cryoscopic constant. Cryoscopic constant. This cryoscopic constant, this whole term is its molality. Molality, right? This delta TF is equals to, that is KF into, this is molality small m, right? This is a relation between the molality and depression in freezing point. And you can make KF is the subject of the formula here. Again delta TF by, it is a m. Okay, already we know that from this we can write it's a units of KF. Units of KF is equals to, this is a delta TF is a temperature difference. Always we'll write down in a Kelvin. And here molality is the units of molality is a moles per kg, and that kg will come to the numerator. I can write kg for mole for this one, and units of KF is a Kelvin kg for mole is the units of particularly cryoscopic constant or the molar depression constant. We have the relation again here, molar latent heat of freezing. Capital LF is always which is a product of small LF into its molecular mass. So that this KF also again it is purely depends on the only properties of solvent. M2 molecular mass of the solvent, TF naught square, that is in freezing point of solvent, LF which is a molar latent heat of solvent. That means KF for a given solvent. Right here KF for a given solvent is always KF is a constant for a given solvent, because it is only depends on the properties of a solvent. Now come to here LF is a product of which is a gram molar latent heat of fusion into its a molecular mass of solvent. If you substitute this one in the above equation, this KF we'll write this is a KF is equals to, we'll write R T naught F square into M2 divided by, it is 1000. So LF instead of this LF you can write down the small LF into, this is a M2 will get cancelled here, so that we can write KF is equals to R T naught F square divided by, it is 1000 small LF. So this is a relation between the, it's a this is a simple KF, molar depression constant or the cryoscopic constant. Even this is also a cryoscopic constant, this is also a cryoscopic constant, right? So this cryoscopic constant and whenever they have given the gram molar latent heat of freezing, use this formula, and molar latent heat of freezing you can use this formula. Main aspect of this colligative properties is to determine the molecular mass of the solvent. So that we need to write delta TF is equals to, this is a KF into this is a W1 divided by, it is a M1, this is a 1000 divided by, it is a M2, sorry, this is a W2, right? So colligative properties, depression in freezing point is one of the colligative property. The main importance of this colligative properties is to determine the molecular mass of the non-volatile solute. Here M1 is the molecular mass of non-volatile solute. You can make this one as a subject of the formula. You can write here this is a KF into W1 into, this is a 1000 divided by, this is a delta TF into, this is a W2. So this is a formula to find out its molecular mass of a non-volatile solute. You can expand even delta TF also here. Here it is a M1 is equals to, this is a KF into, here it is a W1 into, this is a 1000 divided by, this is a T not F minus, this is a TF into, this is a W2. So this is a formula to find its a molecular mass of a non-volatile solute.